We're all used to measuring things we can see and touch, right? The length of a road, the height of a building, that's easy stuff. But what if I told you that math gives us tools to measure things you can't see? I'm talking about the closeness of two ideas or the relationship between two trends. Today, we're going to dive into the really cool concepts that let us measure the unmeasurable.
So just think about this for a second. We can all figure out the distance between New York and LA. But the distance between two sentences, how would you even start? It sounds kind of impossible, but this is exactly the kind of problem that powers things like Google Search and AI. And the answer all starts with really understanding what distance actually means. All right, so here's our roadmap. First, we'll cover the 3 golden rules that a measurement has to follow to even be called a distance. Then, we'll check out 2 totally different ways to measure physical space. After that, we'll make the big leap into measuring abstract things, like similarity. We'll look at some other cool tools for comparing words. And finally, we'll touch on how to spot when 2 things are moving together, something we call correlation.
Okay, let's get right into it. To a mathematician, distance isn't just a number you get from a measuring tape. Nope, it's a concept that has to play by a very specific set of rules. Once you get these 3 rules down, you'll have the foundation for literally everything else we're going to talk about. First up, we've got symmetry. And honestly, this one's super intuitive. All it means is that the distance from your house to the grocery store is the exact same as the distance from the store back to your house. It doesn't matter which direction you're going, the length of the path stays the same. Simple enough, right? Rule number 2 is called separation. This one says that the only way the distance between 2 points can be 0 is if they're actually the very same point. You can't have 2 different spots in the universe that are 0 inches apart. If the distance is 0, you haven't gone anywhere. And our final golden rule is the triangle inequality. I like to call this the no shortcuts by taking a detour rule. It just means that going straight from point A to point B is always the shortest path. Always. If you decide to make a pit stop at point C along the way, your trip can only get longer. Or, best case, stay the same length. It can never, ever be shorter. So, now that we've got the rules down, let's see how they work in the real world. You might think there's just one way to measure the distance between 2 places, but it actually turns out it really depends on how you plan on getting there. We're going to look at 2 big ways to think about distance. On one side, you've got the as the crow flies path, just a perfectly straight line. And on the other, you have the path a taxi might take in a city laid out on a grid, making all those right-angled turns. Both are totally valid ways to measure distance, but they measure very different journeys. Let's start with the one we all learned back in school, Euclidean distance. This is your classic, straight-line path between 2 points. It's the shortest possible route you can take, the one you'd measure with a ruler. It's the path a bird would take, completely ignoring any buildings or obstacles in its way.
Now, this is where it gets interesting. Let's talk about Manhattan distance. Picture yourself in a New York City taxi. You can't just drive diagonally through buildings, right? You have to stick to the grid of streets and avenues. So this distance is calculated by just adding up how far you travel horizontally and how far you travel vertically.
Okay, this is where we take a huge conceptual leap. We've seen how we can use coordinates to describe physical locations on a map. But what if we could give ideas coordinates? What if we could actually map out sentences and documents in some kind of abstract space? Well, that's exactly how we shift from measuring distance to measuring similarity. And we can do this with an amazing tool called Cosine Similarity. Now with this, we're going to forget about how far apart 2 things are. Cosine Similarity asks a totally different question. How much are these 2 things pointing in the same direction? For analyzing text, this is absolutely crucial. A short tweet and a long article about the exact same topic might be far apart in terms of word count, but they're pointing in the same thematic direction. And that's what we want to capture.
So how in the world does this work? Let's take 2 really simple sentences. The first one says deep learning can be hard, and the second one says deep learning can be simple. Now to a computer, these are just strings of characters. The first, most important step is to turn them into numbers that a computer can actually work with.
So, how do we do it? We start by making a list of all the unique words from both sentences. Then, for each sentence, we create what's called a vector, which is really just a list of numbers. It's kind of like a checklist. We put a 1 if the word is in the sentence, and a 0 if it's not. And just like that, our sentences aren't words anymore. They're coordinates in a 6-dimensional space. Now we get to apply the magic formula. Don't let the symbols scare you. It's not as complicated as it looks.
Basically, the top part of the formula just checks how much our two sentence vectors overlap, and the bottom part just scales the result so it always ends up as a number between -1 and 1, which makes it super easy to compare.
And the result is 0.8. So what does that even mean? Well, with cosine similarity, a score of 1 means two things are identical. A score of 0 means they're totally unrelated. So 0.8 tells us that even though our sentences have one word that's different, their overall meaning is very, very similar. Pretty neat, huh?
Cosine similarity is an awesome tool, but it's not the only one in our toolbox. Sometimes we need to compare entire sets of items, like say all the movies two people have watched, or even the letters that make up two different words. Let's look at a couple more ways to do that.
Here are two really popular ways to compare sets: the Jaccard Index and the Sørensen dice index. The Jaccard Index looks at the items the two sets have in common and divides that by the total number of unique items they have altogether. The Sørensen dice index is really similar, but the math gives a little extra weight to the things they share. Both are super useful for things like recommendation and...
Let's actually see this in action with the Sørensen dice index. We're going to compare the English word night with the German word Nacht. First, we break each word down into pairs of letters, which are called digrams. As you can see, the only pair they actually share is HT. So when we plug that into the formula, we get a similarity score of 0.25. So not very similar, which, makes sense. And now for a fun callback to the very beginning. Remember those 3 golden rules for what makes a true distance? Well, it turns out that the Sørensen dice index, while it's great for measuring similarity, is not a true distance. Why? Because it breaks the triangle inequality rule. With this measure, a detour can sometimes actually seem shorter than the direct path.
Okay, for our last topic, we're shifting gears one final time. We've talked a lot about distance and similarity, which are all about how close things are. Now let's talk about correlation, which measures how things move together.
This visual here explains the whole idea perfectly. On the left, you've got a positive correlation. That means as one thing goes up, the other thing tends to go up too. Think ice cream sales on a hot day. In the middle, there's a negative correlation. As one goes up, the other goes down. Like maybe the more you study, the fewer mistakes you make on a test. And on the right, that's no correlation. The points are just a random cloud. There's no clear relationship at all. All right, let's wrap this all up with the key takeaways. First, we learned that distance is a really flexible idea, but it has to follow 3 very strict rules. Second, picking the right measurement, whether it's Euclidean, Manhattan, or cosine, totally depends on the problem you're trying to solve. Third, and this is a big one, remember that similarity measures closeness, while correlation measures togetherness. They're not the same thing. And finally, none of this is just abstract theory. These are the concepts that power so much of our digital world, from search engines to Netflix recommendations. And that brings us to a final thought. We've seen how math gives us this incredible lens to see and quantify relationships we could never spot with our own eyes. So the question I want to leave you with is this. Now that you know about these tools, what hidden connections in the world all around you are just waiting to be measured?